Energy storage.
After being fully charged, there is a potential difference, which we will call delta V, between the two plates. Delta V is equal to the voltage supplied by the battery. So you can see we will arbitrarily assign this as 0 and this is plus V, so delta V is V. There's a uniform electric field between the plates, and we learned earlier that with a uniform electric field, delta V equals minus E delta X, where delta X is your change in distance in this direction. This obviously will be true in the case of the parallel plate capacitor because we have a uniform electric field. The electric field is constant everywhere in the gap between the plates. We've learned that already. The electric potential, the voltage, declines uniformly from plus V to 0 within the gap. You can see plus V, 3/4 V, 1/2 V. You can see how that's a linear progression there. On a ruler, this would be 0, 1/4 inch, 1/2 inch, 3/4 inch, 1 inch. Why is that just like that? Well, because of this equation right here. The change in voltage is equal to negative the electric field times the distance you move. Negative means it gets smaller in the direction of the electric field, so you start with a plus V here, and it decreases down to 0 as you go along the electric field line. That's what that negative is for. Okay, and delta X, that's a linear function. So as you go down, let's say we'll just make some numbers up here, 1/4 of an inch, your voltage goes down 1/4 of a volt. You go down 1/2 an inch, it goes down 1/2 a volt. So it's a linear relationship. And what are these green lines? Equipotential lines, which are always perpendicular to the electric field. So hopefully you can see how all the work we spent earlier understanding equipotential lines, the electric field is perpendicular to the equipotential lines, this equation, how it's all coming together as we describe a capacitor. Why did we show the negatively charged plate with a voltage of 0 and not some negative number? Well, actually it's somewhat arbitrary. The important fact is that the difference in voltage here, delta V, is equal to the voltage supplied by the battery. We could have labeled the voltages as shown over here. We could have started at negative V over 2 at the negative plate, negative V over 4, 0, plus V over 4, plus V over 2. We still have the linear progression, and we also have the higher voltage at the positively charged plate and at the kind of the origin of the electric field vectors. The voltage gets smaller as you follow the electric field. Probably because people like positive numbers better than negative numbers, so we showed it like this. But the other way also would have worked. One of the major purposes of a capacitor is to store energy, and it stores energy in the form of the electric field from the positive to the negative plate. We're going to derive that equation now, and we're going to derive it for the parallel plate capacitor, but it will work for any geometric configuration of a capacitor. First of all, how much work would it take to move a single electron between two initially uncharged plates? So after the electron moves, we're left with a positive charge here, a positive ion. Moving the first electron takes 0 work because in the beginning both plates were at the same voltage, they were neutral, and voltage is related to potential energy, which is then related to work. So if you have 0 voltage, 0 energy difference, you need no work to move the electron. However, once this first electron is here, if I want to move another electron, this electron is going to feel a repulsive force from the electron already there. So you need work to overcome that repulsion. That work is provided by the battery. This will provide the energy you need to move the next electron to overcome the repulsion of the first one. Then moving the third, the fourth, the fifth, all the way up to the billionth electron. There's a lot of electrons here. We're just simplifying it so we understand the concept. This battery will attract the electrons, the positive terminal here. Remember, the positive terminal is a longer horizontal line. It will move through the battery and get deposited on the other plate. The electric force is a conservative force, so the work done on this longer path here, as opposed to just going straight through here, is just the same, so we're going to use that as a model. And remember, the electrons can't move directly between the plates. You have all this air here that's insulating it and not letting the electrons go, so we have this wire connected to a battery, to another wire, to the other plate to let the electrons flow. To move that last electron, and we'll call this one the last electron, because as they came down here, they pushed the other electrons out all over the plate. That requires carrying it through a voltage difference of delta V. The capacitor is fully charged, so you have plus V, 0 V, so the delta V is just delta V. The work required to do that is Q delta V. We've used that a few times earlier. The charge on an electron is negative E, and the difference in potential for the last electron is V. The work to move that electron is equal to negative E times negative V, or just EV. The work to move that first electron was 0 because both plates were at the same potential, so to move an electron along an equipotential surface takes no energy, no work. The work to move the last electron was EV. Now the average work to move all the electrons is going to be EV over 2. And we can use that average value because the voltage decreases linearly from the top to the bottom plate. So we can just take an average of the two works and find out that our average work to move the electrons is EV over 2. If I'm now moving a total charge, not just an electron, total charge Q from one plate to the other is given by work equals QV over 2. That energy is now stored in this electric field that was created by the separation of charges. So that is, as mentioned earlier again, that's one of the functions of a capacitor. It stores energy so you can use it at a later time. The energy stored in a capacitor is given by U sub C equals QV over 2. U stands for potential energy because this is energy that we're storing and we can use it later. Q is the charge on one plate. Don't make the mistake of trying to add the charges and get Q plus Q and 2Q or anything like that. We're just interested in the charge on one plate. V is the voltage difference between the plates that is initially supplied by a battery. UC is the stored potential energy. Note, the top plate is charged to plus Q and the bottom plate is charged to minus Q. So the sum of the charges after being charged up is 0, just like it was in the beginning when it was neutral, when it had a 0 charge, due to conservation of charge. We can now use the definition for capacitance, C equals Q over V, which is over here again, and our equation for electric potential energy. And we're going to find two more expressions for potential energy, which will enable us to solve for the energy depending on whether we're giving the charge, the capacitor, the voltage, whatever. So let's take the capacitance equation, C equals Q over V. We'll solve that for V. V is equal to Q over C. We will also solve it for Q. So I have the three different expressions for the definition of capacitance. I will then take each one of these guys and substitute it in to the equation for potential energy. We have QV over 2 here, QV over 2 here. For this first column, we'll substitute in for V. For the second column, we will substitute in for Q. So I'll take you through the first one, and then you can work this on your own. UC equals QV over 2. I have Q over 2 times V. V is Q over C, and I get potential energy is Q squared over 2C. And if I go down this column, I get potential energy is 1/2 CV squared. A 30 nanofarad capacitor is connected to a 9-volt battery. How much energy can be stored in the capacitor? The capacitance is in nanofarads, so that has to be converted to farads. So 1 nanofarad is 10 to the minus 9th farads. Here's our voltage. The capacitor energy equation is 1/2 CV squared. So there's the 1/2. Here's the capacitance, here's the voltage, and make sure you square it. And you get an energy of 1.215 times 10 to the minus 6 joules. A 75 picofarad capacitor has 18 nanocoulombs of charge between its plates. How much energy is stored in this capacitor? We have 2 unit conversions to do here. We have to convert picofarads to farads. 1 picofarad is 10 to the minus 12 farad. And nanocoulombs to coulombs. 10 to the minus 9th coulombs is 1 nanocoulomb. This time we use the capacitor energy equation with charge and capacitance, and that's Q squared over 2C. We plug in our charge, and again, don't forget the square. Here's the capacitance, and here's 2, and we get 2.16 times 10 to the minus 6 joules. A capacitor is being used so that 225 nanocoulombs of charge stores 1.8 microjoules of energy in the capacitor. What is the voltage across the capacitor's plates? We start with the charge and convert nanocoulombs to coulombs. 1 nanocoulomb is 10 to the minus 9th coulombs. And energy, 1 microjoule is 10 to the minus 6 joules. So we use the capacitor energy equation with Q and V, which is 1/2 QV. I typically just remember 1/2 CV squared. Why? Because that sounds like 1/2 MV squared. It's just a way to remember it. And then if you're not given C and V, just remember that C is Q over V. So you can use this equation with that one to come up with this guy over here. So we need to solve for V, and we multiply both sides by 2 and divide by Q. Substitute in our variables, and we get a voltage of 16 volts. These 2 equations are true for all capacitors. We have C is equal to Q over V, and then we have the potential energy, and there's 3 ways to express it: QV over 2, Q squared over 2C, and 1/2 CV squared. The following equation is true for parallel plate capacitors, as it depends on the specific geometry of the parallel plates. Unless indicated otherwise, kappa is equal to 1. So right over there. Combining these equations can be used to solve many problems related to the voltage, charge, energy, and capacitance of a capacitor.